One of the most important problems in computer science and life is the search problem. Where are my keys? Or rather, given a set S, is some element X in that set? It's convenient to assume the elements of the set are indexed by some key, so we can say that S is the set x1, x2, and so on, which reduces the question to, is there some k where xk is our search term? The obvious strategy is to go through each element and decide whether x is that element. In metacode, decide if x equals x1. If it is, we're done. If not, move to the next. In the worst case scenario, we'd need to go through all n elements. So this sequential search takes n steps. On the other hand, suppose that the elements of our set have a definable order and that our set has been put in order. In other words, given any element x and xi, we can decide whether our search term is less than or equal to xi, and our set has been put in an order where x1 is less than or equal to x2, which is less than or equal to x3, and so on. If this is the case, we can perform a binary search. In human terms, decide whether x is in the first half of the set or the second half. This gives us a smaller set that x could be in, so decide whether x is in the first half or second half of the smaller set, and then lather, rinse, repeat. It's a little harder to decide how many steps this will take, so remember, concrete never hurts. Let's consider a concrete example. And remember, you can assume anything you want as long as it's explicit. Since we're going to be constantly having the size of the set, let's start with a set that contains 2 to the 4th 16 elements. And so our set elements are, again, assumed in order. So we want to decide whether our search term could be in the first half, x1 through x8, or in the second half, x9 through x16. Now, since the elements are assumed ordered, we can decide by comparing x to the 8th element. If x is greater, it's in the second half. If it's less, it's in the first half. And maybe we're fantastically lucky and it is that 8th element, in which case we've found it and we're done. Now, in the best case scenario, x is that 8th element and we're done in one step. But remember, we want to assume the worst case scenario. So again, we can assume anything we want to as long as it's explicit, so let's assume that x is less than x8, and so we know it's among these elements. Again, we can decide whether it's in the first half, x1 through x4, or in the second half by comparing it to x4. If it's greater, it's in the second half. If it's less, it's in the first half. And again, we won't assume we're so lucky as to have it actually equal to x4. Now, before we go on, note that if x was greater than x8, so it'd be in this half of the set, we could do the same thing. In other words, we can decide whether x is in the first half or the second half. The difference here is we need to figure out that the comparison should be to this element x12. But again, let's assume that x is less than x4, so we know it's in these elements. So we'd compare it to x2. And if we assume that x is less than x2, then we know x is in x1, x2. And at this step, x is either equal to x1 or it isn't in the set. Note that the basic step remains unchanged. We're checking to see if x equals xi for the middle value of I in the current set. In this case, our steps were, is x less than x8? Is x less than x4? Is x less than x2? Is x less than x1? At the end of which we had a definite answer of whether x is in our step. So this required n equals 4 steps. And note that if we'd done a sequential search on a set with n equals 16 elements, it would have taken us 16 steps. And so the binary search is 4 times faster. Or is it? What if we had more elements? If we had n equals 32 elements, our questions might be of the form, is x less than x16? Is x less than x8? Is x less than x4? Is x less than x2? And is x less than x1? And in general, if our set had n equals 2 to the power k elements, then we need k steps. So the number of steps will be the log to base 2 of n. Now, note that unless n is actually a power of 2, this won't be a whole number, so we'll need to round it. And in this case, we have to round up, since taking a fraction of a step is the same as taking a step. And so the binary search on n elements actually requires the ceiling of log 2 of n. Generally speaking, any search problem is going to be on large sets. So if n equals 1,000, the sequential search will take 1,000 steps, while the binary search will take 11, so it's about 100 times faster. And if n equals 1,000,000, the sequential search will take 1,000,000 steps, while the binary search will take 21, so it's nearly 50,000 times faster. Or is it? We'll take a look at that next.